Okay, so this presentation is on stream type determination, and I just want to back up for a minute. Actually, all these presentations this morning, I know they feel like overview, and in some cases they are, but they are also part of the Wyoming user manual. So that user manual starts with an overview of the stream functions pyramid framework and the stream quantification tool. There's a section on reach breaks. This part is new, the stream type determination. It's in the user manual, but it also, this isn't really review. This is something that we have changed as a result of just lessons learned and SQTs being used. So why do we need to do it? First and foremost, it is to improve communication. As we had SQTs getting used, people were using, primarily the big issue was proposed stream type and reference stream type were getting mashed together, sometimes used to mean the same thing, sometimes used to mean something different. And then of course, we've got proposed condition, and how does that relate to a stream type? So we just put this together to try to improve communication, first and foremost. And then number two, to make sure that the stratification of entrenchment ratio and pool spacing ratio happens correctly. So that's keeping the reference condition aligned with the reference stream type, keeping our SQT stratification logic pure, if you will. And then if you're just wondering why the Rosgen stream classification system, we use this stream classification system because it is the most widely used stream classification system across the country in both restoration and mitigation. Okay, so there are four, I was going to say four stream types. That's the wrong way to say it. There are four types of stream types. There are four categories of stream types that we want to talk about: existing, design, proposed, and reference. So existing is the stream type that is before an impact or restoration activity. Design is the stream type that will be constructed. Proposed is your stream type that you expect to occur at the end of monitoring. And then reference stream type is the stream type that would naturally occur given the valley morphology and absent from anthropogenic influences. And I'm going to just walk through each of these and give some examples, and that's the extent of this presentation. All right, so the first one is existing stream type. This really is the easy one because you're going to go to the field, take measurements as part of your existing condition assessment, and determine what that existing stream type is. And it correlates with the existing condition assessment in the SQT. It's not used in the SQT, but we do have a place for you to report the existing stream type. So then if you're reviewing the condition scores and you just want to know, well, what stream type do these condition scores align with or represent, then you can see that in the where you enter your data information on the stream quantification tool worksheet. And so here are some examples, of existing stream types. The two on the left are quite common in the restoration world. Many of us are working in incised channels first and foremost. So a G5 little c or a G4 little c, very common existing stream type. A lot of times these G's will erode and widen out and become F's. Also a very common urban existing stream type that we have to work on. But they could also be C's and E's. Sometimes people think of the C and the E stream type as being a design or a proposed stream type, but they can be unstable, they can lack habitat, and so they can very much be existing stream types as well. All right, so next is the design stream type. That is part of the design process. This is the obvious one. It can be the same as the proposed stream type, but it can also be different, and I'll give you some examples of that in just a minute. So this is the stream type that will be built. It's also the as-built stream types. So I did not call out as-built as different. So design and as-built are kind of used interchangeably here. So back to kind of the examples, we might have this existing G5 little c, and we're proposing to design a C5, and here's that C5 under construction. So the proposed stream type is the stream type that is expected to form or evolve to by the end of the monitoring period. This evolution idea is why the proposed stream type might be different than the design stream type. It does correlate with your proposed condition score or your proposed condition assessment in the SQT. And then, as we mentioned, it can be same or different than the design stream type. So here's an example where design stream type equals proposed stream type. Back to our little G, our G little c is our existing stream type. The design and the as-built is a C. And for this particular project, the expectation was that the proposed stream type would remain a C. So we're thinking that this stream type will remain. And just a reminder, if everybody could check to make sure you're on mute. I think we got one person maybe not on mute. So in this example, proposed equals design, meaning that we expect after 5 years of monitoring that this stream type will not change. An urban example, often the expectation here is that design and proposed will not change. You know, there's so many constraints in these urban systems that what is designed and built, we kind of have to make it to where it doesn't change. So another example, design stream type equals proposed stream type. For this, the stream type is a B little c, so different valley type than what we just showed. Now, many times in restoration, what we design is not what we think will be the proposed stream type. It is very common in alluvial valleys for practitioners to design a C with the intention that it will evolve into an E over time. So here's an example of a project that did that. The existing stream type was an F. The design and the as-built was a C. You can kind of see this meander bend. There's a little bit of a bankful bench here, not much vegetation, point bar laid back. And within 5 years, this width has narrowed mainly because of deposition on the point bar here. And there is a riffle around the corner. That width to depth ratio in the riffle was also narrowing. That's really where you do, I'm showing pools, but you do stream classification in a riffle. Those riffles were also narrowing over time. Same process as this point bar. Over time, those banks that are laid back accumulate with sediment from flow events, and those banks will become more vertical. And so the width depth ratio changes from maybe a moderate width depth ratio like a C to a low width depth ratio like an E. So very common in the stream restoration world to do this. So your existing, in this example, your existing, your design, and your proposed are all different stream types. And again, this is just for communication. The SQT is not using any of this information. You're just using it for communication purposes. So this is where things change for the SQT, and that is with the reference stream types. So this is the stream type that would naturally occur in a given valley type absent from human influences. And it's really, in the Wyoming SQT, it's just used for 2 metrics, the entrenchment ratio and the pool spacing ratio. So I just want to highlight that. Like if you're feeling like this is a big influence on the SQT, it's not big overall, but it is big for these 2 metrics, in particular entrenchment ratio. And towards the end of the presentation, I'll give you an example of how this plays out. The other reason we do this is to ensure that 1.0 is pristine. It holds the SQT logic. The problem we've had is that people have used proposed stream type to equal reference stream type, And this is a problem primarily in urban streams where you end up just building a little bit of a bankfull bench and saying you have pristine floodplain connectivity, when we can all look at it and know that is not pristine floodplain connectivity. So that is one of the primary problems we're trying to solve with this little framework. And just a note that reference stream type may be the same or different from the design and proposed stream types. So I just wanted to go ahead and pose this too, because what if I've been showing a lot of C's and E's, and I know that many of you are working towards doing projects that are more like a DA. So a DA in the Rosgen classification is synonymous or analogous to an anastomosed system that folks are starting to design more frequently. We are not prepared yet to put a DA reference stream type in the SQT, simply because we don't have the data yet. We don't have reference curves for these metrics for DAs. And so for now, just select a C or an E. And, before you get too bent out of shape, again, just recognize this is only influencing the entrenchment ratio metric and the pool spacing ratio metric. And really, for these systems, only the entrenchment ratio metric, because you wouldn't do bed form diversity anyway. But we'll cover that in a future presentation. And I also want to just kind of offer a bridge, if you will, from where we are today to where I know folks want to get to with the DA or anastomosed, and that is with a high width to depth ratio C in a low energy environment. So we've done this and it has worked. So I kind of show you an example where we've got an existing stream. This is a G little c or just an incised E. Very low slope, less than 0.1% slope. So that would be a C little c minus. And we go with a high width to depth ratio to create a high water table. The higher your width to depth ratio, the lower the depth, the higher the width to depth, the higher the water table, if you can maintain that high width to depth ratio. And then there's an acknowledgement that, beavers are going to come into these systems. So if you let that happen naturally, over time, it will probably evolve into a DA. And we've seen that. So this is an example where, just the point being, if you leave it on its own, a single thread channel in that environment, low energy, low sediment supply, will likely evolve into an anastomosed on its own. So I've shown these two pictures a lot already this morning. I'm going to show it some more. So here's that existing condition. This is upper coastal plain of North Carolina, if anybody care. Here's the existing condition. Here was the existing stream type, proposed condition or as-built condition. This is just like a few months after construction. And then we just recently came back to this site. It was 20 years later, we came back and walked this site. And this, I can't say that this picture is this exact meander bend, but it's close. And so you can see what this section looked like 20 years later. Like, we're pretty fortunate here that we can grow a forest in 20 years. I know not Wyoming, you're not going to grow a forest as fast as we are, but the point being is that there were sections of this project that remained single thread, but highly functional. There were sections of this project that evolved into an anastomosed section. There was really no discernible channel throughout this particular reach. Water spread all the way across the valley width. And then we found some reaches where there was active beavers and a beaver pond. And so I know that there's interest, a lot of interest in right out of the gate getting to this. My point here is that that's fine. I'm supportive of that. We're working towards getting there, but just to acknowledge that, if you have to start here, it's kind of okay, and just let it evolve to that. 20 years isn't that long when you take 20 and divide it by perpetuity, which many of these projects are protected. If they're a mitigation site with a conservation easement, they're protected in perpetuity. So that's a pretty small fraction of time. So just wanted to kind of make that point, just again to hopefully kind of build a bridge between where we are today with the SQT and where we know people want to go. All right, so kind of back to these stream types. This is that same site where design equals proposed equals reference. I know I just showed you anastomosed in a beaver pond section, but just upstream of this project was a very mature old forest with a very nice single thread channel. So that was our reference. And so so the design of a C equaled the proposed of a C equaled the reference of a C. This is where life is easy, no conflict in the SQT when proposed and reference are the same thing. This is where it gets more challenging, is when design equals proposed but does not equal reference. Your job with the SQT is to enter the reference stream type. So again, this is primarily a problem or an issue for those of you working in urban environments. So we have this F existing stream type. The design and the proposed is a B little c. So this on the ground picture is taken from this bridge looking upstream. So that structure here is this structure here. So you can see there's a bankful bench. You know, we did the best we could. There's a greenway here, a road here. There's a sewer line running somewhere through here. So that's about as much floodplain as we can get. But when we look at this aerial and we look at the valley type, this is the valley. You can see the hill slope on this side. So it sort of stops here, but this whole side is or was an unconfined alluvial valley. So that reference stream type, and this is in North Carolina, we've done a lot of reference reach work in valleys in this part of the state. We know that the reference would have been an E. And so you can communicate to people that your existing is an F, your design and your proposed is a B little c, but in the SQT, you would need to pick that reference as an E, and that's the reference curve that will be used for your entrenchment ratio and your pool-to-pool spacing. And here's why that's important. I'm hoping everybody will be on board with this logic, even though it might not give you the score that you want, but I'm hoping that everyone can kind of agree with the logic. So here's the same picture for the existing condition. Again, another urban stream, because that's primarily where this will play out, and two different restoration approaches. So for this project, the upstream end had more constraints. There's a road on this side and a basketball court on this side. Here's a footbridge. So upstream of this footbridge, all that could be done is a bankful bench on both sides. So the design stream type was a B little c. But again, it's an unconfined alluvial valley. The reference stream type would be an E. So when we pick that E stream type and we put in an entrenchment ratio of 2.0, it scores this B little c against an E, because that's what it should be. And our index value is 0.6, which, by the way, is not that bad. That's the high end of functioning at risk. When we got downstream of this footbridge, we had a lot more room to work. And so we could excavate a valley and build a floodplain. And so here, the design stream type was a C. The proposed stream type was an E. We expect this to evolve to an E. The entrenchment ratio is a 10, and therefore the index value is a 1. We have achieved pristine floodplain connectivity downstream of the bridge because we could excavate a floodplain. So where we hear pushback is when people do this, they'll say, we did the best we could do, so give us full credit. And the SQT does not work that way. It is going to compare your restoration activity to that reference condition. And by the way, you still got functional uplift here. There is more floodplain connectivity after compared to before, but we can all agree that there is way more floodplain connectivity here for the same site. So shouldn't this lower right picture have a higher uplift score than this picture? And of course it should. So that's the main reason that we have put this together. And on that soapbox note, I think I'm done. Oh yeah, and there's the flood going through there, so you can see the floodplain doing its job. All right, so that is all I have.